So let's take a look at an example. Here we want to find the area of a parallelogram in two-dimensional space, determined by two vectors u and v. So we just explored how to do this. We can find the area of a parallelogram in two-dimensional space by just taking the determinant of the matrix, where the columns of the matrix are the vectors that determine the parallelogram. Okay? So the first column will be vector u, negative 2, 1. The second column will be vector v, 4, 3. And by the way, it could also be the rows of the matrix, since the transpose of a matrix, the determinant of the transpose is equal to the determinant of the original. So if I swap the rows and the columns, it'd be the same thing. Okay, so if I take the determinant here, I get negative 2 times 3 is negative 6. Minus 4 times 1 is 4. So negative 6 minus 4, that is negative 10. Now that doesn't make sense as an area. It's a negative number. You can't have a negative area. All right? We'll talk about the importance of that negative number later. In summary, if we think about the matrix as a linear transformation, the way it's transforming the space involves something flipping, and that flipping makes things negative. That's what that negative is encoding. But we just care about the area. We just care about how, if we think about it as a linear transformation, it changes the area. And so negative 10, the absolute value of that will be our area. So the area of a parallelogram is the absolute value of the determinant of the two-dimensional vectors that determine the parallelogram. So the area of this particular parallelogram is 10.